So we were somewhere here, right? 5.7, and we were also doing questions from the
Yeah, we
right
were
exercise.
yeah.
Yeah, right. So we'll go further, but first let's continue this. Okay. And let me see if I've okay. So I'll just pick. Okay. Hmm. So I think let's come back and anyways, yeah. See, so we have some questions also here. Okay. But I think instead of this, let me yeah, this is better if I transfer from here because there I have kind of solved few things. So we can start fresh here. Okay. So let's go back to some of these questions, okay, for whatever we have done so far. Okay. So, and let's see what kind of questions we are getting. Okay. So I gave you that 1, 2, 4, 3. So see, this was a question. Okay. What is the work function of the metal if the light of wavelength 4000 angstrom generates photoelectron of velocity from this? Okay.
Okay.
Work function is the minimum. And then we can do this. Okay, we have that minus 13.6 energy of the level, right? Z square by n square EV, right?
What?
Okay. These are the two formulas for any level energies. Okay. This is in joule. Let's
What's
go
that in?
joule. Okay.
What's that in?
Yeah, I'll tell you. So Z is atomic number. We'll come to this. And N is number of orbit. Okay. N equal to 1, 2, 3, 4. So orbit. The same N which we are using there, 1 by n square, 1 by m square, right?
Yeah.
Yeah, it's the same thing. Okay. So we'll just get into this a bit. Okay. And let's first see what we can do. Okay. From here. These are some questions. And so first let's get back to this one, right? We were done here and I'll add one page here. Okay. So now we'll discuss first and then we'll go there. See, so whatever we are discussing so far, right? I won't derive it for a moment, but let's just see what I'm trying to do. See, there are energy levels, right?
Yeah.
Okay. One, two, and then gap starts going down. So n equal to 1, n equal to 2, n equal to 3, n equal to 4. So as an electron is in these levels, it has certain energy associated with it. Now, Bohr says, according to Bohr's theory, okay, first angular momentum is quantized. So mvr is equal to nh upon 2 pi. Okay. H is Planck's constant. N is equal to 1, 2, 3, 4. It depends. Okay. Energy level. Got it?
Okay.
Okay. R is the radius. V is the velocity. And M is mass of electron. Okay.
Okay.
You have heard about angular momentum?
Yeah, somewhat.
Yeah. Yeah, just this formula is there and we. So anyway, so what we need to keep in mind is this. First of all, that energy of the nth orbit is equal to minus 13.6 z square by n square in electron volts. Okay. And Z is equal to atomic number, N equal to number of level, we'll say. Okay, which level it is in. This is the energy of this. There's a fancy way of writing this also. It is like E naught Z square by N square EV. So E naught is equal to, this is the ground state energy of a hydrogen atom and an electron, right? If Z equal to 1, it implies hydrogen atom, right?
Mm.
N equal to 1 means ground state, right?
Yeah.
So this 0 point energy will be equal to E0 is, we write it as minus 13.6 electron volt, right? Because if we'll calculate from here, right, it will be minus 13.6 and Z is 1, N is also 1. So this turns out to be minus 13.6 electron volts, right?
Yeah.
So for the first level, right? Here I had to write actually 1. So, and this is called actually E naught, right? This is a convention where we call it the 0 point energy. Okay. So it is the first energy which we call E naught. Okay. It is denoted as E naught. I should write it maybe E naught, I think. But anyways, this is the first energy, and which this is a fancy way of writing that this is E0. But main thing is that we need to know this formula. So from this formula, I can calculate the different energies, right? Let's box this and let's say for hydrogen atom, let's talk for hydrogen atom. So energy En is equal to minus 13.6 Z square by N square. This is the general formula, electron volt. Now I want to calculate for hydrogen atom for the first level. So Z is equal to 1, right? For H atom. It's the first element, right?
Yeah.
So the formula will become minus 13.6 by N square. So E1 will become simply minus 13.6 1 square by 1 square EV. Minus 13.6 electron volts. E2 will become minus 13.6. Z is again 1 square by 2 square EV. 13.6 by 4, this become minus 3.4 electron volts, right?
Yeah.
Quite sharp fall, huh?
Yeah. Oh, yeah, actually.
Yeah. And minus 13.6, 1 square by 3 square EV. And this I have to calculate. Let's see how much it is. 13.6 by 9, huh?
Yeah.
13.6 divided by 9. 1.511. So 1.51 minus 1.51 electron volt. See how fast it is dropping, right? And as just a formal calculation, I'll calculate E4 minus 13.6, 1 square by 4 square EV. And now it will go to something 0.13.6 by 16, right?
Yeah.
And this is 0.85 electron volts. So this is minus 0.85 electron volts. See, this is how sharply the energy levels are falling, right? So it's like E1 will be here. Let's say 0 point is somewhere here. Okay, this is 0. Okay. At n equal to infinity, it will be 0, right?
Yeah.
Okay. So here, let's say it is minus 13.6, and then it is somewhere here, it is minus 3.4, let's say. This gap is. And after that, it is minus 1 point. So gap is roughly 10, and now it is 2. See, the gap has decreased so much, right? From
Yeah.
10 to 2, roughly, right?
Yeah.
The gap between these two levels is approximately 10.2 electron volts. And the gap between the next two levels is, right, it's like almost 2, right? Nearly 2, 0.98 something. Right? So the gap has become 1/5, right? Right? If it is 10 centimeter, then I have to like 2 centimeter I have to give. See. The next will be further closely spaced, right? Something
Yeah.
like this, right? Because the variation is by 1 by n square, right? Right. So this is called the ground state. And n equal to 2 is called the excited state. Okay. So n equal to 2 is first excited state. Okay. Got it? Makes sense?
Yeah.
Right? Because n equal to 1, it can only, right? N equal to 3 is second excited state. Excited state. So a common error is when in the question they say second excited state, we, we use n equal to 2. This is a common error. But here n should be equal to 3. Got it?
Yeah.
Right? This is a common error because immediately the brain goes like that.
Yeah.
So next, let's consider helium. So for helium, Bohr's model is not applicable, right?
Yeah.
Not applicable because it is applicable only to single electron systems. Only single electron systems. That's what Bohr's model can do, right? So
Yeah.
helium we cannot do. Helium plus we can do, right?
Yeah.
Here only one electron, right? Because we have knocked out one electron, right? So Bohr's model is applicable. So for helium plus, Z is equal to 2, right?
Yeah.
So let's calculate the energy. En is equal to minus 13.6 Z square by n square. EV. And Z equal to 2. So E1 is equal to minus 13.6. Z is 2 square by 1 square EV. So we can calculate 13.6 into 4. E2 is equal to minus 13.6. 2 square by 2 square EV. So this is just minus 13.6 electron volts, right?
Right.
And E3, we will stop at E3 now. Minus 13.6, 2 square Z square by 3 square EV, right? And we have to calculate whatever the value comes. Let's calculate 13.6 into 4. 13.6 into 4 is 54.4 electron volt. So this is minus 54.4 electron volt. Okay. And this will be divided by 9. So it is 6.044 electron volt. Okay. Now you can
Yeah.
again see the sharp drop, right? Right. So now let's move on finally to lithium. Can we apply
For lithium ion, right?
Bohr model?
No. I mean, no, we can't. I mean, we can because the second shell.
Answer is no. Since lithium has 3 electrons.
Yeah.
Okay. Got it?
Yeah.
We cannot apply to helium. We can apply to helium ion. Okay.
But doesn't lithium have only one electron in the second shell?
No, 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 no. Total electrons. Okay.
Okay.
3 electrons you cannot apply. Now, can we apply Bohr's model to lithium plus?
No.
No. Since 2 electrons. Question. Can we apply Bohr's model. To lithium 2+.
Yeah.
Yes. So let's start. En equal to minus 13.6 z square by n square. Okay. Right.
Mm.
I will start with E1. So Z is equal to 3, right, for lithium?
Yeah. Yeah.
This is whatever EV this turns out to be. E2 minus 13.6, 3 square by 2 square EV.
Yeah.
And E3 is equal to minus 13.6, 3 square by 3 square EV. So this is minus 13.6 electron volts, right?
Mm.
Got it?
Yeah.
Okay. So the first one is 122.4.
Yeah.
The second one is divided by 4. 30.6. See, fast drop, huh?
Mm.
Right?
Yeah.
Imagine your score dropping like this, huh?
Mm.
Then we are able to appreciate it more, huh? The
Yeah.
dropping.
Probably.
Right. So that is how. Right. And then finally 13. So this is how we are. So see, Avika, what we are essentially saying is there are levels, right?
Mm.
I really wish you could draw levels just like that. But anyways. So, okay, let's try to draw levels. So I have this level. I will draw another level. And then I'll draw the third level just to show that decrease is very sharp. Okay, so now what's going on is that when an electron is absorbing energy, okay,
Yeah.
somewhere here, okay, when an electron is somewhere here at n equal to 1, n equal to 1, n equal to 2, n equal to 3. So when this blue is not very nice, I want a light blue, even lightish. So this electron here, if it absorbs energy, it'll jump higher, right?
Yeah.
That's clear, right?
Mm.
So if it absorbs energy, it goes up. And after absorbing energy, when it drops back,
It releases energy.
right? Yeah, it releases energy, right?
Yeah.
After when it drops, it releases energy in the form of,
Right.
yes, right? Electromagnetic radiation, right?
Yeah.
Let's use red. Instead of this straight line, I think I should use this. Is there anything? No. I should have given curves also, but anyway. So when it drops, this is electromagnetic radiation, right?
Yeah.
Electromagnetic radiation. Say electromagnetic with frequency nu. With a certain frequency, right? Got
Mm.
it?
Yeah.
Okay. Clear?
Yep.
So these are n equal to 2 and n equal to 2. So in general, we are going to say that this energy difference corresponds to delta E, right?
Change energy. Yeah.
Right? And this delta E should be equal to
HB.
The energy is conserved, so whatever it has lost, it has appeared. It's the same
Yeah.
thing, right? You go to a hotel, you spend the money, it has disappeared from your pocket, but it will appear in the pocket of the hotel guy, right?
Yeah.
So it is the same energy has appeared in the form of light, right?
Hmm.
We can
Oh,
also write it as hc by lambda, right?
yeah.
So after
Hmm.
certain rearrangement, I can write it as lambda is equal to hc by delta E,
Yeah.
right? And if you, okay, let's now do some thing. So if it is higher level N2 and this is N1, then En2 minus En1. Okay.
Hmm.
So En2 will be equal to minus 13.6 Z square upon N2 square
Yeah.
minus of minus 13.6 Z square upon N1 square.
Hmm.
This is in EV we are doing, right? So this delta E is equal to actually 13.6 Z square into 1 by n1 square minus 1 by n2 square,
Yeah.
right? So now lambda is equal to hc upon delta E, right?
Yeah.
So I can write this as hc and I can substitute this for delta E, I think,
Hmm.
right?
Yeah.
So 13.6 z square into 1 by n1 square minus 1 by n2 square, right?
Hmm.
Let's take a reciprocal. It implies 1 by lambda is equal to 13.6 z square by hc.
Hmm.
And then this will go like this, right?
Right.
It's the same formula, right?
Yeah.
Because everything 13.6 h and c will be constant and everything, right?
Yeah.
Right? You're getting the point, right?
Yeah.
Okay. But here I think I've made one small small thing, which is that I should have taken the energy in what do you call, in joules, so that I could have done this, right? Because I've taken it in electron volt, so I have to convert everything. But anyways, I wanted to illustrate a point, right? Okay, in joules, this is like, so I'll just modify this. But in joules, if you have to write, okay, see, 1 electron volt, I already told you, is 1.6 into 10 to power minus 19 joules, okay?
Hmm.
See, one electron, charge on one electron is simply 1.6 into 10 to power minus 19 coulombs, okay?
Yeah.
So this is same energy unit. When one electron is accelerated through a potential difference of 1 volt, then you get this much energy. That's all. Okay. So in terms of joule, this is minus 2.18 into 10 to power minus 18.
Hmm.
Okay. Z square by n square. And this is the joule. So actually this 1 by lambda thing will, we can, yeah, from here, I'll just write this as some constant. And this also some constant, which is minus 2.18, right?
Hmm.
You're getting the point, right?
Yeah.
So I'll just, how do we rearrange this now? Because anyway, slightly. Minus 2.18 into 10 to power minus 18. Minus 2.18 into 10 to power minus 18. And so this will be minus 2.818. Oh, sorry, it will be plus 2.18 into 10 to power minus 18. So here also it will be 2.18, right? Here also it will be 2 point, because I'll tell you, right? I just wanted to show you from there where that 1 by lambda thing is coming, okay?
Hmm.
Okay. So this is 2.18 into 10 to power minus 18. And I think 2.18 will appear where? 1 by lambda. Here it will appear. 2.18 into 10 to power minus 18. See? Okay. So this has appeared. So 1 second. I just check. And we can do the EVs also.
Okay. So, but I'll show you how to do the shortcut in calculation. So this is how we are getting that formula. You can see the symmetry, right?
Yeah.
Okay. So this is one more bigger formula, but I don't want to derive it for the meantime. So in essence, now I'll just put this line here. Okay. So see, Avika, how do we have to do the questions? Huh? See, we will simply calculate the delta E. Okay. So delta E will be simply 13.6 z square 1 by n1 square minus 1 by n2 square, right?
Yeah.
In electron volts. And then immediately I will get lambda in nanometers by using 1243, right?
Mm.
Right?
Yeah.
Provided delta E is given in electron volts. Got it?
Yeah.
Okay. So I'll just illustrate this also. See how we'll calculate. So let's say it comes from say n equal to 4 to n equal to 2. Let's say it is H atom only. Let's say it is helium plus. So helium plus ion. It is helium plus ion. Okay. So they ask that say electron is dropping, okay, from this to this, and obviously some electromagnetic radiation is getting generated.
Mm.
So we have to find the lambda for this, suppose. So what we will do? So first, we'll simply calculate the difference in energies. So del E will be 13.6 z square. Z is 2 for helium.
Yeah.
We put the full formula first. So 13.6, 2 square. And what is the lower level?
1 by 2 square. 1 by 4 square.
Right?
Yeah.
So if I multiply this, 4, this will be 16, 1 by 4, 3 by 4. Right?
Yeah.
So if this I do, it 3 is a 12. How much we got? 3.02 electron volts, right? I think I started remembering it now. 3.4. 13.6 by 4 is...
10.2.
Anyways, how much it is coming? 4, 3, yeah. 3.4 into 3, 10.2, right?
Mm.
Got it?
Yeah.
See, 10.2 electron. So lambda is how fast to calculate, huh? See? Nanometer, huh?
Mm.
So we can roughly approximate this also. Just divide by 10, huh? 124.3 nanometer approx. It'll be off a bit actually, 121 something, I think. Let's check. 1243 divided by 10.2. 121.86. So let's cut this and write 121.86. See? Right?
Mm.
So these are the questions which are asked. Got it?
Yeah.
So this is how the variation is. Okay, got it?
Yep.
Simple. Okay. Now, now we'll come to this. And now you start doing, do the fourth one and tell me the answer and then we'll proceed. I ordered gulab jamun.
Yum. It's C.
Coming out to be C, huh?
Yeah.
Let me check. This is fourth, right?
Mm.
4C, yeah. Okay. I'll just do the Bohrs for the moment and then we'll switch back.
Hey, can I use the washroom for a sec?
Yes, please. You don't have to ask, you can use.
Yes, sir. What do I do now?
14. One or more than one correct option, maybe. You have to check.
Is the answer A?
Only one option is correct, huh?
Yeah, I think so.
Yeah, it can be. And they say that More than one option is correct. It does not mean that it has to be. So, yeah, maybe. One sec, let me check. Yeah, I think only one will be correct. They are asking for only for hydrogen, right? Yeah, A. Okay. Now you're getting the hang of it?
Very well, yeah.
Okay. See, so these are IIT JEE problems. Let's do some more problems and see. We'll come to this later on. But see, they'll keep on repeating whatever the questions have appeared in IIT. Now they will ask in JEE Main. Okay.
Oh,
Got it?
yeah.
So that is how things are working. Let's see 16th one. Same, huh? Same question, huh? Right. Almost. Light variation.
Yeah. It's C, right?
See. Okay. Now see. Okay. Yeah, first do this. Try this. So wavelength of light required to excite an electron in from this to this level will be. So we simply calculate the delta in EV and we use the 1243. Huh? Got it?
Oh, yeah.
And we get the answer in nanometer. We don't have to go with these lengthy calculations. Are you getting it?
What's the 1, 2, 4, 3 thing again? Lambda is equal to uh, energy.
Energy and wavelength are inversely related,
Yeah. So,
right?
yeah.
So you can either write this or you can write this,
Oh.
right?
Okay, yeah.
Right?
Right,
They're
right.
probably right. It is just, see, let me tell you. We know that delta E is equal to hc by lambda, right?
Mm.
In SI units, I can also make this one some constant values, right? Because we can multiply and see this will come out to be some number, right?
Mm.
Into 10 to power 8. It'll turn out to be something. Let's see how much it turns out to be. 6.626 into 3. 19878. Huh? Oh, sorry. I've done some mistakes. 6.626 into 3. So it is 19.878. Huh?
Mm.
Okay. And everything. So this is an SI number, right? So now if I want to use the energy in joules, let me try divide this or multiply this by 1.6 and then see what I get. No, divide by 1.6. Okay, so whatever number is, if we divide this by 1.6, then we get 12.423. Now you're getting
Yeah.
1242. It is only 1243, not also. It is 1242 only, actually.
Mm.
So that is the shifting, which that is just the adjustment which they have done. Okay. That if we take the energy in electron volt, then corresponding factor will come in and so on and so forth, right?
Mm.
So that is how they have adjusted. So the base idea is that what we do is we simply calculate that energy and then we are done. Okay, delta E and then we can calculate. And this is actually coming out to be 1242.4. 1242.4 it is coming. So yeah. 1242 it is, not even 1243. So we can find the delta E, right?
Mm.
Delta E will be how much in electron volt?
I got a really weird number.
Don't worry, don't worry. How much is this in EV? 10.2, huh?
Yeah.
Sure.
Wait.
So lambda will be in nanometers. What we will get? And it will be 1242.4 or what 242 divided by 10.2, right?
Yeah.
This is in nanometer. And this is approximately equal to 124.2 nanometer.
Mm.
Okay. So which is the one is that is close, and this is in nanometer, right?
Yeah.
So it means into 10 to power minus 9 meter, right?
Yeah.
So this means 1.24 into 10 to power minus 7 meter, right?
Yeah.
Which is the closest. You don't have to calculate even, right?
Yeah.
Get it?
Yeah.
Because the options are given, you just go to the closest and you just simply see it, right?
Mm.
Got it?
Yeah, I got it.
Yeah, we don't have to calculate. The key point is we are not supposed to calculate here, right?
Mm.
Got it? That is the game. Try this one. So here we know that wavelength is about 900 nanometers. So we can calculate the delta E.
Yeah.
And then we can see which of the options A, B, C, D is corresponding to that energy level in EV.
Mm.
Right?
Yeah.
Got it?
Actually, could you explain again?
Can you see? 12th one, 12th.
Yeah, yeah.
Okay. Clear?
Yeah.
Okay. Do it, do it. Easy.
I got delta E, but I don't know what to do after that.
What is delta E? How much?
138.11 into 10 to the power 7.
No, no, no. Delta is 900 nanometer. Okay, let's check. 1243. Delta E you will get in EV.
Yeah.
1243 by 900 you will put how much it is coming.
I did it in meters.
No, 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 no. Why we are doing all this then? Right?
Yeah,
Got it?
that makes sense.
Okay. Again do it. Okay. See, because else it will be quite lengthy, right? And we are susceptible to errors. Here we are doing it so quickly, right?
Mm.
Right?
Yeah.
We just need EV. Why do we need to do what it is given, right?
Mm. I got 1.3811.
Okay, now, and that is in electron volt, right?
Yeah.
So we have to check that which of these transition corresponds to the difference in energy of 1 point whatever you got. Got it?
Okay.
Got it?
Yeah.
From infinity to 3, how much is the energy level? It will be energy because this is 0 and 0 minus this will be 13.3 square EV. How much it is coming?
15.11.
Sorry?
1.511.
Is it the same as yours?
No, I'm getting
Okay.
1.3811.
Okay. Then we go to some other. Let's go to the first one. So the first one difference will be 13.6 and 1 by 3 square minus 1 by 5 square. How much is this?
16 by 25. No.
Yeah. Do it, calculator. I think this is it.
I got 0.967.
Eh. Okay, let me check. For the first one, which is this. The gap is 1.38 electron volt, right? And this is 13.6 into 16 divided by 25. 8.7 something we are getting here, right?
It should be 225, right?
Yeah. 9 and 25. Yeah. 16 by, okay, yeah. 6 divided by 9 divided by 25 into 6. And then it is not coming, I think.
So it's 13 into 16 divided by 225. Like 225.
Yes. 13, still it is not coming, I think. 13.6 into 16 is this. Divided by 225, it is coming out to be 0.967. Okay. So again, it is not that, right? Because
Yeah.
we are getting 1.38, right? This is the. Anyways, so I think what they will mark it around to be is that yeah, for this, but it should come around that, right? We are not getting any value which is like this. Let's see. Uh, and in B, how much we are getting? 13.6 divided by 9. So yeah, B is the closest. Simple, right? 1.38, so 1.5, right? So yeah, we can use B, right?
We use 3 as n, right?
Yes, in B, right?
Yeah. 1.511.
Yeah, we can use this, huh? Right?
Yeah.
This is the closest, right? So we'll use this, huh? Got it?
Yeah.
Okay, because see what is going on. Heat treatment of muscular pain involves radiation of about this. So which is suitable, right? So it will suit it, right? It is closed, right?
Yeah.
Got it?
Yeah.
So that is how we are doing it. Okay. Now let us do some these are some questions. So let's start with 91. Okay,
Yeah.
do it. And again, you can do this after this 90. Again, you don't have to do by this method. We can just use our method, right?
Mm.
The same principle, huh? Every time it is dropping, it will release and we'll calculate delta E and we'll use lambda in nanometer 1242.4 by, right?
Mm. So what's erg, like ERG?
It is 10 to the power minus 7 joules.
Okay.
You can start from 89, 90, 91. Yeah. See, you could have known that what is an erg. If En in ergs is given as minus 2.17 into 10 to the power minus 11, right? Erg, right? Right? Yeah?
Yeah.
It is 21.7, so I have written as 2.17 into 10 to the power 1, so it will become 10 to the power minus 11 instead of 10 to the power minus 12, right?
Yeah.
So this is the thing.
Mm.
And I also know that in joules it is minus 2.17, actually 2.18 it is, but okay. 10 to the power minus 18 joule by n square, right?
Yeah.
So from here I can get the relationship between joule and erg because they have to be same, right?
Yeah.
So we can say that 10 to the power minus 11 erg is equal to 10 to the power minus 18 joule, right? You multiply both sides or whatever do. So 1 erg is equal to 10 to the power minus 7 joules, right?
Mm.
Got it? You can do it. Okay. Oh. Everybody is falling sick. Bad
Yeah.
weather.
Yeah.
Dangerous weather. Not bad.
But it's kind of nice. Like
Yeah,
aside
yeah, yeah.
that from the sick part.
Yeah, except for the sick part, this is the best weather. I mean, I'm not liking it because I'm sick, but it's beautiful weather actually. So what's your brother doing? He's in which grade? Sixth.
Yeah.
So what is his studying these days?
He goes to Chetan's class and he's like, today he's starting trigonometry and he was so excited about it.
Okay, nice, nice. But you stopped teaching him,
Yeah, I couldn't tolerate it anymore.
huh? Uh,
So the answer 3.249.
Answer is
3.249.
what?
Uh, 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 I think angstrom.
Why are we suddenly in angstrom? And which question? 89, right?
Yeah.
So 89, you just calculate the energy required and then they use that. You just don't tell in first get in nanometers.
Yeah.
How much?
324 into 10 to the power minus 2.
No. I doubt it. Just
But then
use
what?
our funda. Excuse me. Okay.
Yeah.
What is the delta E we are getting? 3.4, right?
I got 3.8.
How come? 13.6 divided by 2 square, right?
Yeah. Oh, I was doing using the energy En is equal to.
No. See, I'm teaching you something, huh? Okay. And we are practicing that. Okay.
Okay.
Whatever they are giving, it's okay. We have to do by our method. See, I'm just trying to teach you one concept, that is delta E. We have to calculate in EV and then we use that lambda 124, 2.4 or 1243, whatever, by delta E. So we get in lambda in nanometer, right?
Yeah.
Okay, that's it.
I got 364 nanometer.
How much?
364.
Yeah, that is correct. 364 nanometer. Now, can you convert it into centimeters?
Yeah.
Try. Tell me how much.
Zero point 0.0000364.
Do it in the scientific notation.
Oh. Uh, 3. 364 into 10 to the power minus 7 centimeter.
3 point?
364 into 10 to the power 10 raised to minus 7.
3.36 or 3.6 something you read.
3.6 only.
3.6 into 10 to power?
Minus 9.
Minus 9.
No, sorry, minus 5.
Yeah, minus 5.
Yeah.
See, from nanometers, you can immediately convert into 10 to the power minus 9 meters, and then you can go to minus 7, right? From meter, you can go to centimeters, right?
Yeah.
Multiply by 100, right?
Is it 121.5 nanometer with 90?
How much?
21.5.
Yeah, around 122 nanometers, right? Right?
Yeah.
Okay. Yeah. That is it. Great.
For 91, is it 656.34?
656. Yeah, around about 660. Yeah. Okay.
Yeah.
See how easy it is becoming, right?
Yeah.
Got it?
Yep.
Do 86. Longest wavelength means minimum energy, right?
Oh, yeah, sir.
Lambda equal to hc by delta E. So we have to calculate the minimum energy gap, right?
Right, which is between the two consecutive thingies.
Yeah. So calculate the longest wavelength of the electron from the third Bohr orbit of the helium plus ion, right?
It should be 4, right?
Yeah. So it is no. If it is an electron which is dropping, then I think we have to take
Doesn't
it
say drop-
from 3 to 2, right? No.
It doesn't say dropping though. It just says find the longest wavelength.
No, it is saying, see, calculate the longest wavelength of the electron from the, actually, they should have phrased it better, actually, but anyways, calculate the longest wavelength of electron from the third Bohr's orbit of the helium plus ion, right?
It should be 2.
Right? 3 to 2, right?
I'm getting 656.335 nanometer.
Yeah. Do 84. Then do 85.
I got the wavelength as 486.17. But
84.
yeah.
See, they are asking what transition in the hydrogen spectrum would have to have the same wavelength as the Balmer transition and equal. So for helium plus, they are telling you, right?
And
And uh, you have to find out from which orbits it will drop, right? From which orbit to which orbit it will drop in the hydrogen atom to have the same wavelength as it is having in the case of n equal to 4 to n equal to 2 in helium plus. Okay, got it? See, for 84, huh? It is asking which is having the same. So there are many ways to do it. One is actually, if we also include the z square, then 1 by lambda formula becomes this. Huh? Okay. So 4 to 2 was for helium, right?
yeah.
First write the formula here. N1 square minus N2 square. So for helium plus, 1 by lambda is equal to RH, right? 2 square into 1 by 2 square minus 1 by 4 square, right?
Yeah.
For hydrogen, 1 by lambda, because the wavelength is same, right, is equal to RH into 1 square, right?
Yeah.
And we have to find out N1 square minus N2 square, right? So these two things must be same, right? This and this, right? So above thing I can write as RH into 1 by 1 square minus 1 by 2 square. I have multiplied 2 squares,
Yeah.
right? Got it?
Yeah.
And this should be equal to 1 by N1 square minus 1 by N2 square.
Yeah.
It implies which transition from 2 to 1 for H atom, right?
Yeah.
Got it?
Okay, yeah. Thank you.
You can do it like this, or we can do it like this. That delta E in this case will be 13.6 Z square 1 by N1 square minus 1 by N2 square, right?
Yeah.
So for helium plus, delta E will be equal to 13.6 2 square, right?
Yeah.
1 by 2 square minus 1 by 4 square, right? And this will be somewhere equal to 13.6 into, I can again write this as 1 by 1 square minus 1 by 2 square, right? Clear? For the hydrogen, this is for helium plus, right? Now for hydrogen, we don't know the levels, but the energy difference should be 1 by N1 square minus 1 by N2 square, right?
Yeah.
So from here, the energy should be same because the wavelength is same. So again, we are getting the same result, right? Right?
Yeah.
Got it?
Yeah.
So that is how it is.
So can you scroll up?
So you understood 86, right? Oh, 84, right? Now 85. Here we have to calculate Z, right?
Yeah. So for the 85th one, I got a really odd number.
Okay, it's okay. You won't get great numbers here.
No, it's like really not possible.
What are you getting?
It's like 2 lakh.
Okay, no. Then it's a bigger. You see, first you have to calculate delta E, right? Delta E equal to 13.6. You see, you know the wavelength, right? In nanometers.
Why do we have to calculate delta E? We can
You
just,
know the nano wavelength in nanometers, right?
yeah.
Right?
I think it was that only because I wasn't taking it in nanometers.
How much nanometers?
30.
Huh?
It should be 30, right?
30?
Yeah.
Well, we divide this by 10 and multiply by 10, right?
Yeah. Okay.
So yeah, 30 nanometers, huh?
Hmm.
So what is the delta E corresponding to this? One, two, four, using that.
Yeah. 41.433.
How much?
41.433.
41.
Yeah.
Okay. Now that should be, now we have got the delta E, right? That is in electron volts, right?
Yeah.
So now what we will do?
Equate, like form the equations and equate them.
13.6 Z square into 1 by 1 square minus 1 by 2 square, right?
Yeah.
And that's it. Delta is equal to 13.6 Z square into 1 by 1 square minus 1 by 2 square. You know the delta E, you have to calculate Z.
Approximately 2.
Yes. Now you're getting Z equal to 2, right?
Even before I was getting it is equal to 2-ish, but I think I didn't take it in nanometers. Otherwise, I would have gotten 2. Yeah.
So Z equal to 2 means which species?
Helium plus ion.
Yes, right?
Yeah.
So that is the game, right?
Yeah.
Helium plus ion. See? Wow, nice. 86 now?
I think we already did this.
86 we have done. Okay.
Not
Then 81st.
No. Actually, we have, I think. Hmm. Getting 364 nanometer.
Shortest wavelength means maximum energy, right?
Yeah.
Okay. I think this will be correct. Great. So yeah, we have kind of done a lot of this. 73. Try 73. See, all will do this by 1, 2, 4, 3. First, we will know that what is the energy of this wavelength, right?
Okay, yeah.
In electron volts, right? And if this energy is greater than the required energy, then we'll be able to eject the electrons, right?
Yeah. But can you repeat that?
You think?
Yeah.
No problem. No problem. Oh, mama. Yeah.
Is there 5 metals?
I don't know.
Wait, I
Check.
forgot. Important to electron volt.
You're getting 5, huh?
Let's check again.
Yeah, check. First check what is the energy of this. And whatever it wants to knock out, it should have energy less than or equal to that, right?
Yeah.
Right? Right?
Hmm. Is it still 5?
No, check again. What is the energy you are getting?
4.1433.
So 4.1, right?
Yeah.
So which one are less than 4.1? How many?
4. Oh, right. Yeah.
Right?
Right.
Got it?
Yeah. What now?
We have 5 minutes. So you see, these are right. These are IIT JEE advanced problems, huh? Subjective problems we did, right? Okay. These questions. Okay.
Yeah. They're not easy.
Huh? Sorry?
They're not that easy.
Hey, come on. Why come not that easy? You did almost all of them, right?
Yeah, but it made me think a lot.
But and you are in class 9, dude. 10. Okay.
Mm.
So that is it, right? You have to think like that, huh?
Yeah. It's really fun.
It's just, see, we just did one concept and it's like we are studying and studying. It's like, okay, give yourself time, okay?
Yeah.
You cannot be like that, okay, sir, I went for 2 classes in guitar and now I'm not John Bon Jovi, huh? Okay? You can't
Yeah.
do that, okay?
Yeah.
So please, lower your expectation and increase your hard work, huh?
Yeah.
Not the other way around, huh? Okay. You still did great. I mean, obviously, you needed some input, but yeah, see, that is what I wanted to show you, that these things are not that difficult or something like that. It's like the same thing. They will keep on repeating the same thing. And once you are done with your 10th, again, you'll read in 11th. You know, and obviously, you'll understand more, right? Okay. That is the game.
Yeah.
You don't have to be like this. You should be happy because,
Hmm?
of course, you need certain uh, input, right?
Yeah.
You need certain work, but still, see, you were able to pull out, I mean, almost except one, I think. You did almost everything, right? So that is the main thing which you have to see. And these you are able to do. See, you have to do that same thing. You have to do that energy in EV, and then we have the formula. Okay.
Yeah.
You can revise and then we can continue. We can stop here for today. Okay. It's not a problem. Right. Okay.
Hmm.
Chalo, theek hai. Okay, we'll continue this, and in the next one we'll start with these formula. Okay, wave like, and then we'll do more questions on these. Okay.
Okay.
Yeah. You don't have to worry. You did good, according to me. You did very well. Okay. And the same thing, you see. Huh? So you can do these 5.112 and send me. Okay. Got it?
Okay, I will.
This. Mm. Yeah, these are enough for okay.
Okay.
Okay, Avika. See you. And now the time has changed, and I think I have pinned it also.
Hmm. Okay.
Okay, chalo. Bye. See you. Bye.